for joining. Well, my name is Nuno. I'm an Android developer at Critical TechWorks. If you don't know, we are a BMW joint venture put together to build software for BMW. And in these 3 years, I've been working mainly in BMW's Android automotive infotainment systems. So we do cool stuff with Android, and that is actually how this session came about. So the plan for today is to demystify KSP. So you guys are probably already using libraries in your projects that support KSP. And if you're like me, you've probably wondered what is the black magic going on behind the scenes. So today we'll see exactly what that magic is all about. And we'll also learn that KSP is in fact a surprisingly simple API. My goal is that by the end of the session, you'll have the necessary tools to start using KSP in your projects and also conjure your own KSP magic. Okay, I must warn you that, however, we have a lot of ground to cover today, so we'll be moving quickly. Also, the code snippets that I'll show you are part of a working demo app, and at the end I'll provide you the link so that you can dive into the code at your own pace and revisit everything that we'll talk about today. So, what's on today's menu? First, we'll start by seeing what KSP is and how to use it. And then the best way to really learn KSP is by actually using it. So we will solve 3 practical problems with KSP, each with increasing complexity. This example should cover everything that you need to get started with KSP. And let's now see what is KSP. If you go to JetBrains' website, it will tell you that it is an API to develop compiler plugins focused on Kotlin and with simplicity in mind. Let's dissect this in a bit more detail. So KSP is a tool to analyze and manipulate Kotlin code, which opens the door to implementing our own compile time tasks, such as code generation and code verification. It is also a faster and more efficient alternative to CAP, in some cases up to twice as fast. And the big thing about KSP is that it understands Kotlin-specific features, such as top-level functions, extension functions, and more. Let's also see what is a compiler plugin. So, a compiler plugin is a metaprogramming tool that enhances our programming experience by extending the capabilities of the compiler. Plugins call the compiler directly as a library to analyze and, in some cases, even edit the original source code. The end goal is to usually create some output, such as boilerplate code. As you can see, compiler plugins are pretty powerful things, but power usually comes at a price. So to develop a full-fledged compiler plugin, you usually need a lot of background knowledge on the compiler and on the specific compiler implementation. This means that your compiler plugin will often be tied to a specific compiler version. So if you want to update the compiler in your project, you will probably be forced to update your plugin. And the Compose compiler plugin is a prime example of this issue. But fortunately, KSP is different. KSP is designed to abstract the implementation details of the compiler so that you don't need to worry about changes across different compiler versions. Also, KSP is not tied to the JVM, so you can use it, for example, in Kotlin multi-platform projects. KSP also is focused on performance, and probably the biggest design decision behind KSP was to trade complexity or to trade the power of a full-fledged compiler plugin for simplicity. So KSP provides a simplified API, which is actually very similar to Kotlin Reflect. And the trade-offs are that with KSP, we cannot examine expression-level code nor modify the original source code. So we can only do additive transformations of the source code with KSP. These design decisions should, however, not deter you in any way from using KSP, as KSP is usually more than powerful enough for our applications, with, of course, the added benefit of a much gentler learning curve. And don't take my word for it. Trust all the popular libraries that currently support KSP, and this list is only increasing by the day. So, let's have an overview on how to use KSP. We start by creating and registering a symbol processor with which we collect and analyze Kotlin symbols to generate some Kotlin code. To create the processor, we start by implementing the symbol processor interface. And by the way, most things in KSP start with a dedicated interface. Our processor usually has a few important properties, such as a code generator to create files, like Kotlin files, a logger to log whatever we might need while KSP is calling our processor, and in some cases, even the options that the developer might have set while configuring the KSP Gradle plugin. An interesting fact is that KSP does not directly instantiate our processors. We must instead create a symbol processor provider, which KSP then uses to create instances of our processors. Again, we start by implementing an interface, which expects us to implement the create method, in which we return an instance of our processor. This method gives us access to the environment in which KSP is running and allows us to extract some useful information, such as the code generator, the logger, the user-defined options, but also other things like the Kotlin language version, the compiler version, the platform, and more. Then the next step is to register our processor provider so that KSP knows how to call our processor. To do that, we add this file to our module resources under this folder. This file contains a list of the fully qualified names of all our processor providers. And a word of warning, if you are anything like me, you will eventually forget to add one of your providers to this list and probably waste hours of your time trying to understand why KSP is not calling your processors. However, I am glad to announce that we now have a better way of registering providers. So you just annotate them with the auto-service annotation, which comes from this Gradle dependency. And then there was a nice guy, I don't know him, but he did a really nice job of creating a KSP processor that actually generates that file that we saw earlier for us. All we need to do is to add his processor to our project. And when we apply the KSP Gradle plugin, we get access to this KSP function, which then we can use to provide all the Gradle dependencies that implement KSP processors that we want to use in our project. Okay, next we need to collect and analyze Kotlin symbols with our processor. And we do this by implementing the process function, which gives us access to a resolver. The resolver is our ticket into the Kotlin compiler and how we will collect the symbols. You should also know that KSP actually works in multiple processing rounds. So please be prepared for your process function to be called multiple times. In each round, this function should return a list of all the symbols whose analysis you might want to defer to another rounds, and we will see this later. Let's now see how we can collect symbols with a resolver. So say you want to collect all Kotlin files. All you need to do is call the getAllFiles method, and this returns a sequence of KS files, which is again an interface that represents a Kotlin file. If you are wondering why the method returns a sequence, please bear in mind KSP is focused on performance, so most of the collections that you get with KSP are lazy. However, most of the time, you actually want to collect symbols that are annotated with specific annotations. So for this, we call the getSymbolsWithAnnotation method and provide the qualified name of the annotation. This returns again a lazy collection of all the symbols annotated with that particular annotation. To be honest, I think having to provide the qualified name of the annotation as a string is a little error prone, so let's create a nicer version of this function, which instead uses the clay class of the annotation directly to retrieve its qualified name. So now this is how we collect symbols with my annotation, and we can even create other functions to help filter the kinds of symbols that we want to collect. For example, we might collect only annotated classes, annotated functions, properties, and so on. Okay, I will not go today into the details of how KSP models the Kotlin language, but I just want you to have an idea that KSP follows Kotlin very closely. So you will naturally start to understand this mapping as you use KSP. For example, you have multiple interfaces that represent the different kinds of declarations you have in Kotlin. For example, class declarations, function declarations, but other things like property declarations and more. all of these interfaces implement another interface which represents the declaration of just a generic Kotlin symbol. However, we also have other things like declaration containers. A Kotlin file is an example of a declaration container. But so that you have a sense that all of these actually make sense, if you think about it, a class declaration is also a declaration container because we can in fact declare properties, methods, and even other classes inside the class. But in the end, all of these entities are KS nodes. A KS node is literally a node in the tree that KSP builds while analyzing the source code. This is not exactly the abstract syntax tree that the compiler creates, but it is a tree of symbols that is closely based on the AST. Well, because declaration containers are all Kotlin symbols that can be annotated with an annotation class, they also implement an interface, KS annotation, that represents just that. Well, each of these interfaces we see here provide a simple API to analyze each kind of Kotlin symbol. For example, this is the API to analyze a class declaration. As you might expect, you have access to the class kind, its primary constructor, its supertypes, which includes the interfaces that the class might implement, and also its base class, and more. If you are curious, you have here in this link the complete KSP class diagram. Just be prepared because it is a big one. As another example, here is the API to analyze function declarations. What's interesting about all of these interfaces is that they only provide you an API to analyze the attributes of a symbol declaration and not its actual implementation. For example, with the KS function declaration interface, you cannot actually analyze the body of a function. And this is because the KS prefix in all KSP types stands for Kotlin symbol. And you should really think of these symbols as just the declaration of some Kotlin code entity and not its implementation. As you remember, this is in fact one of the trade-offs necessary for KSP's simplicity. So the last step in using KSP is to generate some juicy Kotlin code. And we could have an entire session on this, but we don't have time today. So I'll just advise you to please be as lazy as possible and do not generate code manually. So use a library instead. I think that Kotlin Poet is an excellent library. It is also very intuitive, so that's what we'll be using today. And we'll learn how to use it as we go through the examples. So let's solve some real problems using KSP, starting with enum classes and seal classes. Okay, our project will be structured in two Java modules, one that contains our annotations and the other which has our KSP processors. When working with KSP, it is always a good idea to start by stating what we want. So, in this case, given an enum with some entries, we want to generate convenience extensions that check if an object is one of those entries. So, we will introduce the case detection annotation to mark the enums which will get these extensions. And since enums and seal classes are actually quite similar, our annotation will also work with seal classes. The only difference is that we will have to use the is instead of the equals operator. So let's now create the case detection process and implement the process function. We start by collecting all the classes annotated with our case detection annotation, and then we filter all symbols which KSP can validate in this processing round. For that, each KS node has a validate method, which checks if KSP has all the necessary information for all subnodes associated with that KS node. For example, if one of those nodes depends on code that we will generate later, KSP will not be able to validate that node in this processing round. Okay, then our process function just returns the symbols which we could not validate in this processing round. And now we need to process the valid symbols. As mentioned, our annotation will work for enum classes and seal classes, and even seal interfaces for that matter. And to process these symbols, KSP uses the visitor pattern, in which a KS node can accept a visitor object. The visitor encapsulates the processing logic for visiting all subnodes of a KS node. And in general, it receives at the beginning of each visit data of type D and returns a result of type R at the end. This is also why we need to provide initial data when the KS node first accepts a visitor. And then in the end, the accept function just returns the accumulated result after visiting the very last subnode. The KS visitor interface, I think, has 25 or so visiting methods to visit each different kind of node. However, most of the time, the visitors we implement don't receive or return any data and are only supposed to visit a small subset of all KS node types. So for this situation, we can instead extend of KS visitor void, which is a visitor that doesn't receive or return anything and has an empty implementation for all visiting methods, so that we only need to implement those that we really have to use. Okay, we will now implement the enum case detection visitor, and because of time, I'll let you check in the demo app the implementation for the seal class visitor, but it's again very similar. Since the visitor will be generating those convenience extensions, it receives the code generator, and because, as I said, it doesn't receive or return any data in each processing round, the initial data is just unit. To implement the visitor, we extend KS visitor void and only need to implement the visit class declaration. Here, we'll extract each enum entry and map it to the convenience extension. So the entries of an enum are actually declarations within the enum class declaration. They're also of type KS class declaration, but their class kind is enum entry. And once we have the entries, we need to start generating some code. As I said, for that, we'll use Kotlin Poet. So some Kotlin Poet 101 for you guys. Kotlin Poet uses the builder pattern extensively. And each kind of Kotlin entity, such as file, function, property, and so on, is represented by a spec. And to create a spec, we need to use a spec builder. And that's pretty much all that we'll need for, all the Kotlin Poet that we'll need for today. So we will need a file to all the code that we'll generate, and we'll start with a file spec, and we'll create it with a file spec builder. Then we'll add the convenience extensions, which are the extension properties. So we call add properties, and we'll provide a collection of property specs, which we will map from the enum entries. And then we just need to build a file spec and write the code to a Kotlin file using the code generator. We also provide a flag to help KSP handle incremental processing. In this case, the output file is only going to be affected by a single input file, which is the file where we declare the enum. This means that our processor is what we call an isolating processor, so it just means that we can set the aggregating flag to false. To create the builder, we only need to provide the package and the file names. The package name will be the same of the enum, and the file name will just be the name of the enum with the case detection suffix. Then let's finish our visitor by creating the property specs for the convenience extensions. Okay, we'll map the enum entries to property specs, and because these are extensions, we need to add the enum as the receiver of the extension property, and we'll also need to add an implementation for the getter. To create the builder, we need to provide the name of the property, which is just the name of the enum entry plus the is prefix. The type is a Boolean, and then we make sure that the extension has the same visibility of the enum. So if the enum is declared as internal or public, the extension will have the same visibility. Okay, to add the receiver, we just convert the enum class declaration to a Kotlin Poet class name, and then we implement the getter using a getter builder. For this, we only need to provide the code that does the entry checking. And also note that we can use this placeholder to interpolate the enum entry. We only provide the entry as a Kotlin Poet class name to Kotlin Poet, and Kotlin Poet does interpolation for us. Finally, we build the getter, and that's it. We are then solving our first problem for the day. Let's now move on to the main course, where we'll create some view models that play nice with Compose. In this problem, we will use Coin for dependency injection, and we will use pure MVVM, so we won't be dealing with things like UI state, data classes, and so on, just for simplicity's sake. So imagine you are creating a weather app that shows weather details for various locations. You probably want to start by showing an overview of the weather for each location. So the composable for the overview might have a view model that looks something like this. And then the composable will get the view model instance using an injection function. To preview the composable, you need to override the injection function and provide an instance of the view model which is appropriate for previewing. That usually means creating mock data and using mock services or repositories. Now imagine you are building the complete details screen, which uses not only this composable, but also other composables that have their own view models. Now you're kind of in a pickle if you want to preview this composable, because you need to add parameters for each view model right in the parent, so that when you are previewing, you can override each instance with your own previewing instances. What if we could solve this problem right at the source? That is, when we declare each of the composables that inject their own view models. For this, we will introduce our custom injection functions, and these composables will also use an interface that defines the view model contract instead of using the view model directly. Of course, both the regular and the previewing instances of the view model will implement this contract. These interfaces will have the sum prefix and will be generated by our KSP processor. So the contract for each view model simply becomes an interface that exposes its public properties and methods. With this contract, our KSP processor can even generate previewing data classes, so that we don't need to have the work of creating mock repositories and mock services. And this is what those previewing instances look like. Of course, our custom injection functions need to get their previewing dependencies from a previewing module. And since Coin has no concept of preview module, I added this small extension to Coin, and you can check in the demo app how I did it. This extension has its own DSL to define previewing definitions, just like Coin has the Coin DSL for Coin modules. As an exercise, you are more than welcome to create a KSP processor that generates this DSL, just like Coin annotations generate the Coin DSL, but that is, of course, another challenge. So for each preview definition, we'll associate the runtime viewModel type with a previewing instance. Then we also need a composable function to call in our previews so that we can provide the preview module. And finally, our special injection functions which can inject the previewing dependencies when we are running under compose previews. So let's now adapt the original composable so that it uses the viewModel contract and our special injection function, and that's it. Well, almost, because unfortunately the injection function is generic on the viewModel type and the contract type. So our processor will also generate an injection function for each viewModel with the appropriate type parameters so that we can simplify the call side. Now, when previewing the original composable, instead of having to provide a previewing instance of the viewModel explicitly, we just wrap it in our Coin preview and provide the preview modules. And this becomes truly elegant for the details composable, because now we can drop all of the parameters and simply wrap it also in our Coin preview. So let's sum up what we want. First, we'll introduce a previewable annotation to mark our view models, and then our view models will implicitly implement the viewModel contract. This implementation is implicit because we'll actually generate the implementation for the contract interface based on the implementation of the viewModel. So, if we add a property or a method to the viewModel, nothing happens to the contract. But if we add the override modifier, then that property or method becomes part of the contract. And of course, this applies to all properties and methods of the viewModel. And lastly, don't forget that our processor will also generate the injection function for each viewModel with the appropriate type parameters. So let's get going and create a processor. Like we did before, we collect the classes annotated with our annotation. However, now KSP will not be able to validate any of these classes because they implement an interface which does not yet exist, which is the view model contract that we will be generating next. So instead, we just keep track of the symbols that we visited so that when KSP does another processing round, we simply ignore them. And then we need to visit each view model with our previewable visitor. It is also a visitor that doesn't pass any data around, so we extend ksVisitorVoid. And once again, we only need to visit the class declaration. Here, we'll extract all the properties and methods which will be part of the view model contract. And this just essentially means that they have the override modifier attached to them. Let's also create a file spec to hold our code for the contract. And then we need to add a type, which is the interface of the view model contract. And we also need to add a top-level function, which is the injection function for that view model. And then we build the spec and write it to a Kotlin file like we did before. Generating the injection function is fairly simple, and because of time, I'll let you check the implementation in the demo app. The interesting bit is actually generating the view model contract. So we'll use an interface builder, and then we add all the properties and methods that we collected in the last step. Again, adding those is fairly simple, so I'll let you check the demo app. And to create the interface builder, once again, we provide a package name and the name of the interface. The package name is the same of the original view model, and the name of the interface is just a view model name with the some prefix. And that's it. We're done with our main course, so I hope you still have some room left for dessert. And I promise this will be a sweet treat because you guys deserve it after all that we've been through. So for dessert, we have content providers. Maybe a tough pill to swallow if, like me, you don't really enjoy working with them. But let's try and add some sugary KSP icing on top and make a sweet dessert. So imagine you need to read from a content provider that publishes a list of locations. Wouldn't it be cool if we could avoid all the hassle of setting a content observer and then having to manually read all, using a cursor, all the content from the content provider columns? What if reading from the content provider was as simple as defining a model class to hold our location data, and then just calling a content observer extension, which returns a flow that lets us observe the content provider rows directly as a collection of locations. All that we need to do is to provide a contract that tells this extension how to read the locations from the content provider. And as you might have guessed, we'll be generating this contract next. Let's first introduce an annotation, the content type annotation, to mark our model classes. And interestingly, this annotation will actually hold some data now, the authority of the content provider and the path to the table we'll be reading from. We'll also assume that the column names of the content provider associated with a model property is the name of the model property just capitalized. So if we are reading from a content provider that has funny column names, we'll also introduce a column name annotation so that we can provide these mappings manually. Okay, let's now analyze the contract that we will be generating. First, we start by adding some constants, and also this contract extends an interface for reading and writing from the content provider. This interface is generic on the content type, which is in this case the location. So the constants that we'll be adding are the authority and path that we'll extract from the annotation we created, and also the mappings between the property names of the model class and the column names of the content provider. Then we need to implement the interface. And the interface has actually quite a few things in it, but these are the two most important ones. So a cursor extension to extract an instance of the model class, which is essential when we are reading from the content provider, and also a function to convert an instance of the model class to content values, which we only need when writing on the content provider. So let's create our last processor. Again, we start by collecting all model classes annotated with the content type annotation. And as in the first example, we only care about the valid symbols, so we just return the ones that were deferred to other processing rounds. Then we focus on the valid symbols, but before we can visit each model class declaration, we need to first extract the data of the content type annotation. So we call get annotations by type to retrieve an instance of the content type annotation. And only then can we visit the declaration of each model class. Unlike the previous problems, now our visitor will actually be passing some data around between each visit. So we introduce the content type context class to hold these processing data, and I will refer to it as just our processing context from now on. And now our accept function will return the final processing context after visiting all subnodes of each model class declaration. In this processor, we don't pass the generator to the visitor because we actually can only build the contract once we have the final context, which is returned by the accept function. So we'll abstract all the code generation logic in a contract builder, which will return a file spec builder with the code for our contract. So all that it's left to do is to implement the visitor. And we now extend from KSMT visitor, which receives a processing context at the beginning of the visit and returns another one at the end. The empty visitor expects that we implement a default handler, which is used, again, by default when visiting all the various types of KS nodes. Here we'll just implement a handler that is a pass-through of the processing context. And then we need to actually override all other visiting methods that have a different visiting logic. So when we visit a property declaration, we'll just add that declaration to the previous processing context. And when visiting the class declaration, we'll collect all properties and then compute the final processing context by accumulating the context returned in each visit of the properties that are declared. Last but not least, we need to return the final processing context so that we can build the contract using our contract builder. And now that we have it, we can go back to the processor and implement the contract builder. We start again with a file spec builder to hold our code, and the package will be the same of the model class, and the name is just the name of the model class with the contract prefix. Again, we add a type, which in this case is an object, so we'll use an object builder. And the name of the object is like the file name, the name of the model class with the contract suffix. And because our contract needs to to implement the content type contract interface, we add a super interface. Also, this interface is generic, so we need to provide the model class as a type parameter. And for that, we use the parameterize by function of Kotlin Poet. Then we need to add the cursor extension to retrieve instances of the model class and the function to convert instances of the model class to content values. Once again, we have nothing new here, so I'll let you check the implementation in the demo app. And now we complete our processor by building the file spec. And that's it. We have completed our dessert. I hope you enjoyed, and this also ends my presentation. Thank you.